Good afternoon. In today's video, we're going to be looking at Dalton's law and partial pressures. So Dalton's law of partial pressures specifically, but we're going to look at both of them separately as well. So at the end of this, you should be able to recall what Dalton's law is and then apply it to a total pressure of a gas in order to determine partial pressures of the individual gases are. And you should be able to recall what a mole fraction is and use it in order to perform calculations using mole fractions, including Dalton's law of partial pressures. So gases can either come as pure gases or they can be a mixture. Almost always our gases are going to be in mixture form. So most times gases exist as mixtures. And it's because they are always going to homogeneously mix when they're put together. So they're really quite easily mixes. And any gas that you introduce to another gas, it's just going to expand throughout it. So they're just going to very naturally mix together. The gas that we breathe in the air is a gas mixture. So our atmosphere. And it includes nitrogen and oxygen, argon, carbon dioxide, and then a whole host of other types of gases are in there that make up our atmosphere. So most of them are gas mixtures. You're going to see pure gases when you actually go to a place to buy gas. So you can get pure gases that have been isolated out using some sort of filtration method. But most of them would be gas mixtures. And the total pressure of the gas is a combination of the partial pressures of the component gases. So the gas pressure of a gas is the sum of the pressures of the component gases. So we call these component gases their pressures. So the pressures of the component gases are called partial pressures. And those partial pressures combine to give us our total pressure. And this is Dalton's law, which specifically says for a gas mixture or a mixture of gases, each gas is going to exert its own pressure. So Dalton's law for a mixture of gases, each gas exerts its own pressure. Okay, so we said that P total is equal to P1 plus P2 plus P3 and so on and so forth, however many component gases you have. And this total is a sum of all of those gases. So if we think about the pressure of our atmosphere, for instance, this is going to be a sum of the pressure of nitrogen, the pressure of our oxygen, the pressure of our argon, pressure of our carbon dioxide, and then all the rest of the gases. But those are the main components. So we could just say that if we were to solve for our atmospheric pressure, we could do the partial pressures of all the component gases to determine that. And it's just a simple sum. So for instance, if we were to add together hydrogen gas with helium gas, keeping the same exact volume, keeping the same exact temperature, if we added them together, then we could solve for the total pressure. So here our partial pressure of H2 is 2.4 atmospheres. Our partial pressure of helium is 6.0 atmospheres. So our P total would be the 2.4 atmospheres plus 6.0 atmospheres, which gives us 8.4 atmospheres of pressure. So very easy. Now, if we're already given the partial pressures, it's a very simple task to just add them together to get our total pressure. But a lot of times what we're given is mole fraction or mole amounts. So let's look at what a mole fraction is. And we've discussed this previously, but we're going to bring it back up. A mole fraction is the ratio of molecules of one component gas, or one component, in a mixture. It doesn't necessarily have to be a gas, but one component in a mixture. We solve for our mole fraction, which is given by this chi here. And that'll be equal to, just say, for the mole fraction for substance A, it'll be the moles of A divided by our total number of moles. So pretty easy, where our N total is equal to Na plus Nb plus Nc, so on and so forth, right? However many substances are within our mixture. And then to solve for our partial pressure of A, it's going to be our mole fraction of A times by our total pressure. Okay? So let's try this out. We've got a mixture of helium, neon, and argon. They have a total pressure of 790 millimeters of mercury. There is 15% argon, 60% helium, and 25% neon. We want to know the partial pressure of each gas. And then we want to know number of moles of argon in 135 liters, assuming the temperature is 295 Kelvin. So this is basically saying that we have a mole fraction of 0.15 for argon, 0.60 for helium, and 0.25 for neon. So these are our mole fractions. So we take our mole fraction, times it by our total pressure. So our mole fraction of argon times by our total pressure will give us our partial pressure of argon. So let's go ahead and just do that. 0.15 times by 790 millimeters of mercury gives us 118.5 millimeters of mercury for the partial pressure of argon. Do the same thing for helium. 0.60 times by 790 gives us 474 millimeters mercury. And then neon, 0.25 times by 790 gives us 197.5 millimeters mercury. And then, of course, we want to round all of these to sig figs. Like so. Now, we want to figure out how many moles of argon we have, where we have a volume equal to 135 liters, a temperature equal to 295 Kelvin, a pressure equal to 120 millimeters of mercury, and we're just going to solve for N using our ideal gas law. So the first thing we need to do is we need to convert this from millimeters of mercury into atmospheres. Which gives us 0.16 atmospheres, and then that can go into our equation. So we're going to be solving for our N, our number of moles. And of course we could have used the Tor one, but I prefer 0.08206. And when we solve for this, we get 0.87 moles of argon.